course, happy to record. Okay, so let's see what we got with 57. Kings won last night. They're in like a four-way tie for fourth place. That's exciting. Okay. Gabriella, sure, you can come in. Why not? Why not? Let's just let everybody in. Water sign. So again, the question was 57 from 4.5. The size of that number means it's probably pretty far into the lesson, so that should be fun. 57. Suppose the function f is continuous on the closed interval from a to b. Under what conditions is the value of a definite integral on f a to b equal to the area of the plane region that includes the graph of f on a to b as a boundary? Explain when the value of the definite integral is not equal to the measure of such a plane region. Yeah, this is a good question. And this is something that we've sort of been tiptoeing around. And it's this idea that the definite integral as a measure of area can be a slightly imperfect concept, precisely because sometimes, and this is what they're asking, it's not going to be exactly equal to the area of the plane region. Because what the definite integral does, that integration symbol means take this infinite sum. And that infinite sum, that Riemann sum, can include negative values. Okay, so if we go to our, what was our definition? So the definite integral is this guy here. So it's the same as the limit of this sum. This f of w sub I can include negative values. And so that's when it's going to break down as a perfect analog to the area of a plane region, is if your curve drops under the x-axis. And that's what we saw with example 2 with the sine curve. In terms of strict geometry, the area bounded by this curve is positive. It's this area plus that area, whatever that ends up being. In terms of our definite integral, however, it's 0 because it drops below the x-axis. And when you start summing up these values, they cancel out these ones. And so the short answer to 57 would be when f of x is less than 0. John?
If the function goes into quadrants 2 and 3, does that automatically make it negative?
If the function goes into quadrants 2 and 3.
Like if it's touching any part of it, does that make the whole thing negative? Like I'm just thinking the cosine function like on the other side of the x-axis, on the y-axis to the left. Is that whole thing negative?
Positive and negative only deals with the x-axis. It doesn't matter in relation to the y-axis. So yeah, the cosine, like, we could draw it here. Pencil. 27. Yeah, because that's a full cycle of the cosine. That's a period of 2 pi. And so it's going to have equal parts above and below the x-axis. Yes. So Sean was curious about 27. And obviously you're meant to graph that. But the cosine function between negative pi and pi is basically the sine function just shifted over. And so that comes out to 0. Good question. Yeah, so I guess specifically, yeah, the value of the definite integral is not equal to the measure of the area of the plane region whenever f is less than 0. or whenever, I guess maybe a more specific way or precise is to say whenever the interval from A to B contains function values that are less than 0. That's a good question. All right, so let's go ahead and jump into 4.6. 4.6 will take us at least the next 2 days. I'm hoping just the next 2 days, and then maybe have Friday as sort of a homework day. But we'll kind of just see. 4.6 is going to be pretty stinking important as we move into something called the fundamental theorem of calculus. Or I suppose the fundamental theorems of calculus. You know, anytime something is called fundamental, it's probably, pretty important. So what we are about to do in 4.6 is cool in its own right, and I think you'll find it interesting, but is most important in its use as a stepping stone in the proof of the fundamental theorems of calculus. Okay? So it's kind of building towards this big aha moment where we're going to see where's this connection between what we did all of first semester and what we're going to be doing all of second semester. And it's the fundamental theorems of calculus. And 4.6, the mean value theorem for integrals, will help us get there. So sometimes we have to do that in math, which can be a little annoying, but it's like we do intermediate stuff in order to get to the main course, as it were. So 4.6 is going to be called the mean value theorem for integrals. And you'll notice that we're specifying 4 integrals because you should hopefully be thinking, mean value theorem, haven't we seen this in our lives before? Haven't we seen this for derivatives? And we're like, yeah, I think we have. So in fact, if we want, we could scooch all the way back to, I don't know what section was that. Well, it doesn't matter where it was. The mean value theorem for derivatives was the idea that, well, let's do this. Where have we seen this before? With the MVT for derivatives. And what did the MVT for derivatives promise us? Well, it said if you had a continuous curve between A and B, it's doing kind of whatever it wants to do. I'll call this f of x. That if you were to draw the secant line between the endpoints on that closed interval, and find the slope of the line passing through those two endpoints, somewhere in that interval between A and B, there's going to be a value on your function whose derivative equals that secant. So guarantees, oh, and I just said guarantee and I can't spell it. That's one of those words that till the day I die will plague me. G-A-U? G-U-A?
Yeah.
G-U-A, guarantee? That looks wrong every single time that I spell it. Guarantees existence of C inside this interval from A to B such that the derivative at C is equal to the slope of this line, which will be given by f of B minus f of A divided by B minus A. And it looks like there would actually be maybe 2 on this interval. It guarantees at least one of them. It looks like we might have 2, but we would just kind of guess it here maybe, because the derivative at C is, of course, the slope of the tangent line at that point. And we can see that there seems to be a parallel tangent line at this point C. Or put another way, there is some average slope, some average rate of change between the endpoints of a continuous interval, and we can find a specific derivative that matches that average. Okay. And so now we're going to do something similar, where we're going to have an average integral. Okay. We're going to have some point in between 2 endpoints where the area underneath that point is going to match the total area of your curve, which is kind of nutty, okay? So it's kind of the other side of this coin. But before we get there, there's a couple stepping stones we got to use. So the mean value theorem itself is kind of a stepping stone to the fundamental theorem. But before we can really grasp what the mean value theorem for integrals promises, there's 2 theorems, I think one of which we'll try to prove, that will help us get there. So we very likely will not actually get to the mean value theorem today, or certainly not prove it today, but we'll get almost all the way there. So the first sort of intermediate theorem before the mean value theorem, we're not going to prove. We're just going to throw it up there and kind of nod our heads and say, yeah, that sort of makes sense, just based on our intuition and the picture we're going to draw. And so this will be theorem 4.6.1. And we'll write it down, but then we'll draw the picture that will sort of elucidate what exactly we're saying. So if the functions f and g, man, f and g are integrable, on the closed interval between a and b. That's the first condition. You gotta have 2 functions that are both integrable. And then the second condition is sort of the important one. And if f of x is greater than or equal to g of x for all values of x in that closed interval from a to b, then the following inequality will be true. That the definite integral from a to b of f of x dx must be greater than or equal to the definite integral from a to b of g of x dx. Which I think on an intuitive level, even without the picture, sort of just makes sense. If f is always bigger than g, then its integral should be bigger as well. But I think a picture is also instructive here. If you want to draw an axis here. A, we've got B, so we've got two curves. Call that one f of x. Call that one g of x. Interval goes from A to B. All this theorem says is that the area underneath g of x, we'll use blue. Do I have blue pen? I did. Here it is. That the orange stuff is more than the blue stuff. Okay. Well, what if these aren't both positive? It doesn't matter. Okay. Because as long as f is bigger than g, the negative parts of f will be smaller than the negative parts of g. Okay. So I think intuitively and visually, this theorem makes sense. And for such a simple theorem, it's a pretty involved proof that involves limits and all sorts of gross stuff that I just don't think adds much to the understanding of the theorem. So we're going to do that. Okay. This will mainly be used in the proof of the next theorem, which I think we actually will prove. So do we have room here? No, we're going to do it on the next page. So 4.6.2. And this one is definitely benefited by a picture. We'll again jot down the theorem first. And then draw the picture. And then I think we actually will prove this one. That's a pretty straightforward proof. So our first condition is we're going to suppose that f is continuous on the closed interval from A to B. If little m and big M, oh, here you come in, sure, why not? Wait, where'd you go? Where'd you go? There you go. If little m and big M are respectively, very respective, you know, if they are the absolute minimum and absolute maximum, so now it makes sense why we had to suppose that f was continuous on a closed interval, because that guarantees the existence of these absolute maximums and minimums. So if little m is the absolute minimum, big M is the absolute maximum on that interval. Then we get to say something sort of interesting that, again, once we draw the picture, I think will make more sense. So the absolute maximum functions on A, B, so that, and then they kind of explain what that means, which is a little unnecessary, but we'll do it anyway. So that M is the lower bound of function values, little m is the lower bound, big M is the upper bound. So f of x is between those two values for all values of x on that interval. This is what it means to be an absolute minimum and an absolute maximum on an interval. It means that your function is always greater than or equal to the minimum and always less than or equal to the maximum anytime your x value is on that interval. Okay? Literally just saying what minimum and maximum means. Well, if that is true, then the following inequality is true. Let's do it. No, it's fine. The minimum times b minus a is less than or equal to the definite integral from a to b of f of x dx, which in turn is less than or equal to the absolute maximum times b minus a. What? So the minimum times b minus a is less than the integral, which is in turn is less than the maximum times b minus a. So we've gone from a bounding of the function by these minimum values and maximum value to a bounding of this definite integral on this interval. So that's sort of interesting. So what does this actually mean? Here it's pretty clear. With this number is always bigger than this number. It's always less than this number. But what are we actually referring to here? Let's draw the picture and we'll see. Get my straight edge. Let's visualize this. Let's say we've got A and B, and we've got some curve going on. So there's f of x. And here's our interval. And so this middle part, the definite integral from a to b of f of x, is this part in orange. Kind of hard to see, but at least I guess we'll do it a little darker. So the orange part is the middle of our inequality from the theorem. So what are the left and the right saying? Well, somewhere on this interval, because this is a continuous function on a closed interval, there's an absolute minimum value, a value that all the rest of the points on this curve between these numbers is going to be greater than. So we can kind of eyeball that. It looks like it's maybe right about here. So if we were to label this, this would be little m. This is the absolute minimum. And it actually appears that the absolute maximum in this case is at the endpoint b, which is incidental, doesn't really matter. And so this would be big M up here. Okay, so we've got the little m and the big M. What the heck is b minus a? Well, b minus a is the distance between a and b. So this distance here is b minus a. So what this theorem is saying is that the minimum value times this quantity b minus a is less than the area under this curve. Well, geometrically, m times b minus a, let's go look at that. M is this minimum value, which is also the height of this rectangle here. So this rectangle has a base of b minus a and a height of m. And so all we need to see is that, yeah, this rectangle here, which I'll use, maybe I'll just polka dot it. So this green polka dotted rectangle, m times b minus a, that area is less than the area under the curve. That sort of checks out. And then the other side is the bigger rectangle that we, in the same way, can make this smaller rectangle with our minimum value and the length of our interval. We can make this bigger rectangle with our maximum value and the length of that interval. And I'll use, I guess, blue for that. And it should be clear that that area in that rectangle is bigger than the actual integral. So the big box is bigger than the stuff under the curve. The little box is smaller than the stuff under the curve. Does it make sense what this theorem is claiming? You good on that? Okay, well, then let's prove this, because it's actually a pretty straightforward proof, I think, in terms of the rigor this year. We've definitely not been doing a ton of proofs, so let's jump in and do it. Porque no. Okay. So here we go. Proof. Let's skip one line. So the first part of our proof is just the fact that because f is continuous on a closed interval, so because f is continuous on this closed interval a to b, that's going to guarantee the existence of absolute extremum on that interval. And that is guaranteed by the extreme value theorem. There's that word guarantees again. Guarantees existence of little m and big M. And so the place we're going to start is with little m. That if we were to integrate some function m on that interval from a to b. Both because we can just see it, but also from theorem 4.5 point something that said if we have a constant as our function, then the area underneath that curve is just that constant times the length of the interval, okay? Which we can visually see here, that if we wanted to call m some new function, the integral from a to b of m is exactly this polka dotted area, okay? And so this definite integral from a to b is equal to m times b minus a. Comes from 4.5.9, but also from just looking at this graph. And in a exact same way, doing the same with our maximum, the area there, that definite integral is big M times b minus a. All right, cool. So basically just saying that we can define definite integrals that have the left and right sides of our integral, or that are the left and right sides of our integral. And then now we get to apply one of our stepping stones. That because m is the absolute minimum of our function, it follows that f of x is greater than m everywhere on that interval. And remember, the very first thing we did today, I guess the second thing we did after we remembered the mean value theorem for derivatives, was if you've got two functions and one is always bigger than the other, you can apply that inequality of the one being bigger than the other to their definite integrals on that interval too. So that's exactly what we're going to do, but now we're going to use f of x and n. Okay. So by theorem 4.6.1, we can say that the definite integral from a to b of f of x dx is greater than or equal to the definite integral from a to b of m dx, because f of x is greater than or equal to m for all x in that interval. Which means, based on this definition right here, that the definite integral from a to b of f of x dx is greater than or equal to m times b minus a. So we're halfway there. We have proved the first half. This definite integral is greater than this one by applying 4.6.1. And then we can do the same thing with the maximum. So in a similar fashion, we can apply 4.6.1 and say that because the function m, this horizontal line, is bigger than f on that entire interval, because it's defined that way, it's the absolute maximum value, the definite integral from a to b of m has to be bigger than the definite integral of f. the definite integral from a to b of big M, our maximum, is guaranteed to be bigger than or equal to the definite integral of f. And then again, substituting this definition, we have that m times b minus a is greater than or equal to that definite integral. And if we call this equation 1, or inequality 1, and this inequality 2, we just combine those and we've arrived at the conclusion. So combining one and 2, we have that m times b minus a is less than or equal to the definite integral from a to b of f of x dx. That was 1, just flipped, which in turn is less than or equal to m, big M, times b minus a, which was 2. Cool. Cool. So what we're going to do now is, I think just one example, and then we might call that a day. Let's do the example, see how it feels. Any questions about this 4.6.2 theorem? Because this will factor heavily into the mean value theorem tomorrow. I think it just kind of makes some sense. So kind of pragmatically, what this theorem allows us to do is, given a function and an interval that we might not be totally confident on what the actual definite integral is, we can establish some boundaries for where it must be. So we can find the absolute maximum and minimum of a given function, and then use those values to sort of bound in possible values of that integral. Okay, and so we'll see that in example 1, and maybe example 2. What's up?
Can you go down to the bottom of that for just a second?
Here?
Yeah, thank you.
Yeah.
Okay.
All right. Example 1. Let's do this. What is example 1? Apply theorem 4.6.2 to find a closed interval containing the value of the definite integral from 1/2 to 4 of x cubed minus 6x squared plus 9 plus 1 dx. Use the results of the example of section 3.4. Okay. So, example 1. We have f of x equal to x cubed minus 6x squared plus 9x plus 1. And we're not being asked to find the integral, but to find the boundaries of the integral on the interval between 1/2 and 4. So the integral from 0.5 to 4 of f of x. We want boundaries. Which means theorem 4.6.2. So what we need, absolute minimum and absolute maximum of f of x on the interval between 1/2 and 4. Which, if we were inclined, we could certainly take the derivative, find out where it's 0, look at the endpoints, and find the absolute maximum minimum. Okay, and that is something that we should be able to do. But we're bailed out because it says, then from example 1 in section 3.4, or use the results of example 1 of section 3.4. So let's see. Would you look at that? We've got this nice cubic function, x cubed minus 6x squared plus 9x plus 1. And in example 1, they do a real nice job. Oh, this is an absolute maximum. This is increasing and decreasing. But they do find the spots where we have critical numbers are at 3 and 1. And the function values there are looks like a 5 and a 1. Okay, so our absolute maximum is going to be at 1. Our absolute minimum is going to be at 3. Or maybe it's 4. I don't know why they sent us there. Anyway, so the absolute minimum is equal to 3. No, sorry, is equal to 1. And the absolute maximum is 5. The absolute minimum happens at x equals 3, but it is equal to 1. That's the trick that, or the stumbling block that I warned you guys about, and I almost just stumbled on it. So now we can use this as our little m, this as our big M, and applying 4.6.2, we can come up with a range of values that this definite integral must fall into. So theorem 4.6.2 guarantees that, and this is A and this is B, that M times B minus A is less than or equal to that definite integral 0.5 to 4 of f of x dx, which in turn is less than or equal to the maximum times b minus a. So now we just plug in our specific values for little m, big M, and a and b. So we have the left side is 1 times 4 minus 1/2 is less than or equal to 1/2, or the definite integral from 1/2 to 4 of f of x dx, which is less than or equal to big M, 5 times 4 minus 2.5. The left side, 1 times 4 minus 1/2, looks a lot like 3.5. On the right side, 5 times 3.5, it's like 17.5. 5 times 3 is 15. 5 times 1/2 is 2.5. Yeah, sure, we'll call it 17.5. Who knows? I mean, I'm sure it's written right in the book in my lap. Sometimes it's fun to do mental math. And so what we've established then is that the interval, or that the integral from 1/2 to 4 of, and we'll write out the whole thing, x cubed minus 6x squared plus 9x plus 1 is somewhere in this interval between 3.5 and 17.5. This little E symbol means is contained in. And if you're kind of like, I don't believe you, Mr. Smith. Oh, and I forgot the dx. Well, we've got technology that can sort of, back us up a little bit.
Mr. Smith.
We can check the numerical integral of that function and just cross our fingers and hope that it's a number between 3.5 and 17.5 and have some faith in the process. So quit. Math 9 brings up the numerical integral. We'll do 0.5 as our lower bound. 4. And we want x cubed minus 6x squared plus 9x. Nope, plus 9x plus 1. And we want that in terms of x. And we're going to press enter and just really hope, orange box, did I do something wrong? Kat wants to know, how did I find the absolute minimum and maximum at the start of the problem? I cheated and the book told me because we had done that problem back in section 3.4. But if they hadn't, we would have had to taken the first derivative, found the critical points, found the values at the critical points, found the values at the endpoints, and picked out the biggest and smallest one. Because that's the process for finding absolute extremum. Check the critical points, check the endpoints, whatever's smallest, I don't know which camera's on, that one. Whatever's smallest is your absolute minimum, whatever's biggest is your absolute maximum. But for the sake of brevity, they gave us the solution, or the extremum here. Oh, and now the suspense is built because we've been looking at this blinking cursor, just wondering what's going to happen when we press enter. What's going to happen? What's going to happen? What's going to happen? Whew, phew. 10.6. Is 10.6 between 3.5 and 17.5? Oh, you betcha. And so we have some reassurance that this theorem is worth its salt. Preguntas, como ejemplo numero uno. No.
I have a question.
See.
How does that value answer the question, or what's the significance of it?
Which value?
The 10.6.
So that is the actual value of this definite integral, which 10.6 is bigger than 3.5 and it's smaller than 17.5. And so graphically, if we were to graph this, yeah, that's actually kind of a good, let's do that. X cubed minus 6x squared plus 9x plus 1, and then we'll also graph 1 and 5. And then see what our window looks like. No, that's kind of gross. We'll take a smaller window there, much less there. Much less y. Let's do like 8. And actually, let's bound this too. Let's just go from 0.5 to 4. So the definite integral, this guy here, is the area underneath this blue curve. and it comes out to 10.6 or whatever. What we did with theorem 4.6.2 was said, hey, we know that that area is bigger than the area of this rectangle, which was 3.5, but smaller than the area of this black rectangle, which was 17.5. Okay, but absent seeing this graph, it can be a little bit hard to agree with that. And so we were just verifying that that actually checks out.
Okay, thank you.
And the reason that we do it is because now we have at least a ballpark for this amount, because we, at this point in our lives, can't compute this. This is not, I mean, maybe you learned this in geometry, but I did not learn how to figure out the area of a cubic function. I learned like circles and triangles and squares, but definitely not areas that look like that. And so you can't just look at that and say, oh, well, the area is this based on my geometry skills. But we can simplify the problem to the kind of just the most simple. This will be the smallest possible. This will be the biggest possible, which means the actual value is somewhere in between. And as we'll see, starting on probably next week, this will turn out to be a pretty simple thing to find. But for now, we're kind of just slowly backing our way into it. Good question. Okay, let's see if what we've done today equips you to do any of the homework. I'm hopeful that it will. We're going to call that good for notes. Let's see, AP Calculus. 4.6, 1, 9, 21, 23, 33, 41, 43, 45. Are any of those achievable with that which we have covered today? Yeah, you can do 1 and 9. Do you want to do that? I'm gonna be mean guy here. So attempt number 1. I'm actually gonna add let's say number 5 and number 9. And 1, 5, and 9. For number 9, it would probably behoove you to take a look at example 2, because it's a trig function, but the idea is the same. Find the absolute maximum and minimum of the sine function on the given interval, and then apply the theorem. So number 1, you're just figuring out which one's bigger and applying 4.6.1. And then 5 and 9 is the application of 4.6.2. Finding a closed interval containing the value of the definite interval. And then tomorrow we will take up with the remaining section, which is the mean value theorem. It's going to be real gas. Questions, thoughts, feelings? All right, Zoomoids, you are welcome to make like trees and get the heck out of here. Cornucopia of confetti from Tasha, thank you. She's excited to leave. Adios.
Bye.
You're welcome.
Thank you.
You guys are also free to skedaddle if you want. And I will see you guys Tuesday, because you guys are done being on campus after today. I mean, hopefully I'll see you in